Okay, so welcome back, everybody. Yesterday, the last lecture, we discussed the four-color problem, the four-color theorem, which unfortunately, you could have a whole you could have like a whole course just about the kind of the progress of that theorem and the proof of it and subsequent improvements and things like that. So we can't, don't have the time to go into all of that, although it's very interesting. But as a result, as an outgrowth of the research that went into working on the four color problem, there's a lot of useful terminology, a lot of useful uh, quantities came out of that. Of those sorts of investigations. So one of them are chromatic polynomials, which originally were an outgrowth of, I believe, Birkhoff in the early 1900s when he was working on the four-color problem, resolution of it. Chromatic polynomials were discovered. So what is a chromatic polynomial? So first, before I talk about them, I have to talk about what I mean by a coloring being different. So question, what does it mean for colorings to be different? So the answer is given some graph G with vertices, say V1, V2, and so on, up to some Vn. A coloring of G, of course, is an assignment of a color to these vertices. So we call colorings C1 and C2 different. So we will call them different or distinct colorings if at least one VI receives a different color in C1 than it does in C2. That seems fair. It seems like an obvious definition if we are thinking of the C1 and C2s as functions, right? Because, I mean, what does it mean for two functions to be equal? If two functions are equal, right, if they're identical, they're the same function, it means that they literally assign every single point to the same value, right? If they differ even at a single point, there's two distinct functions. So if you have two functions, one, take your favorite function, right? Maybe f of x equals x squared is your favorite function. If I take that and I form another function g that is g of x is x squared everywhere except at the point x equals 5, and at x equals 5 it's equal to 0, right? Then even though both of those agree on infinite sets even, right? They agree literally everywhere except a single point, that g function is still a different function. So here, this makes sense even in the finite context that this would be the case. So what does it mean if two colorings are not different? It means they assign the exact same color to every single vertex, right? Or every corresponding vertex. I made it sound like every vertex gets colored the same color. That's not what I mean. So, each v sub I receives the same color in both. That's what it would mean. That's what it means to have identical colors. Okay, so if I were to uh, do this, all I have to do is find a single vertex and color it differently in one, and that gives me distinct or different color. Okay, so then the second question, now that we know this, is what if I ask the question of how many different colorings are there? Like, of some graph G. obviously I'm not going to be able to answer this um, question for generic graph. Well, I should say, I'm going to have to say some things if I hope to do that. Maybe it's best to investigate some specific graphs first. Here, let's do a quick example. Let's say that G is K4. So let G be the complete graph on 4 vertices and say how many different colorings of K4 is there? So how many? Well, this isn't so hard to count, right? So there, of course, is a reason why, like, all these things we're talking about. This is like the 4th or 5th time this has specifically come up. But obviously, in our previous questions about numbers of paths, numbers of cycles, various enumeration problems. Obviously, the combinatorics is coming in, but here you'll especially see it because if I ask how many different colorings of K4 are there, so K4, what does K4 look like? Uh, you could do this without even drawing a picture, just because there's not that many vertices and it's kind of easy to keep track of in your head. But K4, here's K4, right? So every vertex has degree 3. We'll say this is V1, this is V2, this is V3, and V4. Okay, so here's our graph. How many different colorings are there? Well, first of all, I have to ask, how many colors am I using? So first, how many colors am I using? Because that seems to that's going to matter here, right? It's definitely going to affect how many colorings there are. If I'm only using a single color, for instance, there's only one. Then you can ask yourself the question: if you're using 2 different colors, well, then you have to ask: is the thing even 2 colorable to begin with, right? So if we are let's not get into questions about that, so that we can just talk about colorings and not have to worry about how many colors we're going to use. So let's say we use 4 colors. So say we use 4 colors. The reason why, of course, this isn't a crazy restriction is that we have the 4 color theorem, right? And if we believe the 4 color theorem is true, it means that if we have a planar graph, which this is, we have a planar graph, then we know that this thing is 4 colorable. It's connected to planar. It's 4 colorable. So 4 colors is fine. That is definitely enough. So this is fine. So if I'm using 4 colors here, how many colors or how many colorings exist? Or how many different colorings exist, rather. So, well, let's see how this goes. Let's just go vertex by vertex. If I start with vertex 1, what are the number of colors I could possibly assign to vertex 1 here? Well, if I'm using 4 colors, then any of the 4 colors are an option. So I could assign 4 colors, any of the 4 colors, to the first vertex. Okay, but once I've done that, of course, when I go to the next vertex, how many different colorings could I make by coloring the second vertex? So in vertex 1, there's 4 choices I could have made. No more, no less. Like that is that's the maximum number of choices I could make. So that vertex could be any of 4 colors. Once I've done that, though, in V3, because vertex 1 and all the other vertices are adjacent to each other, this really locks down what's going on here, right? So when I go to, say, we'll just go to V3 next. Going to V3 next, how many options are there? Well, any of the colors that I didn't choose on vertex 1 are allowed here. So 3, one less than before. So I chose one color, whatever that color was. I now have 3 colors to choose from for my next vertex that I'm coloring. What about vertex 2? So this is, it's the same deal. I chose a color here, another color here. I have 2 choices left for a color here. And then when I get to my last vertex, this single color I can pick is already nailed in, right? It's already locked in. And so this is the number of different colorings of K4 using 4 colors. Using 4 colors. Okay. What if 6 colors were used? So what if I use 6 colors instead of 4 colors here? Right. Well, let's use the same way of counting. My first vertex, I have 6 choices now. My next vertex, I have 5 choices, right? Any of the choices I didn't make in the first one, right? So in the first one I picked something. I have the remaining 5 colors. For the next vertex, now I have 4 colors remaining. And then for the last vertex, I have 3. Any of 3 options are viable here, right? This is then the number of different colorings of K4 using 6 colors. Well, let's go back to my original question. What if I only use 2 colors? If I only use 2 colors, there can be no proper coloring of this, so 0 is the number of different proper colorings of K4. So, what is it that's going on here? You've likely already seen this just based on probability courses or the amount of enumeration you've already had to do in the past. You probably see what it is. You definitely know what this quantity is, but then you notice what's going on here as well. So, what is this? Well, let's define something real quick. So, define define C sub G of K to be the number of different colorings of a graph G using at most K colors. This is the number of different colorings of G using at most K colors. Now, thus, we've already shown so here's our definition for this C sub G of K. We have already shown that C sub K4 of 4 is 24, right? This is 4 times 3 times 2 times 1. This is 24. We have shown that C sub K sub 4 using 6 colors was 6 times 5 times 4 times 3, which is 360. And we've shown that C sub K sub 4 using 2 colors is 0. It is a fact. You can think about maybe how you would prove this, that if, just based on these patterns you've seen here, it's actually the same proof for the thing you know this is, which I won't say. I'll wait till we get to combinatorics to say it explicitly. So if we'll say K and N are positive integers, then this C sub K sub N of K can be computed as K times K minus 1 times K minus 2, and so on, all the way to K minus N plus 1. Okay. And again, you may recognize this expression from elsewhere in your math career. Okay, if, of course, also if K is less than N, then this number is 0. Also, another fact. So the first thing to stress here, of course, is that this is the number of distinct colorings on a single graph class, right? This is just for the complete graphs on n vertices. You're able to compute this, so obviously the type of graph impacts this. In fact, what is the number of distinct colorings on the empty graph on n vertices using at most k colors? Well, here, because there's no adjacency, I'm free to use whatever colors I want to on each vertex. So at every vertex, I have k choices. So k times k times k times k, and there's n vertices, so k to the n. And this is true for all k and n. So for an empty graph, this is real easy to compute. Okay. Some other facts that you can quickly just unpack from the definition. So here's another one. G is k colorable if and only if so this is only if and only if this number C sub g of k is greater than 0. Right? Consider why this number was 0 in this case, right? For complete graphs. Another fact is that this number is greater than 0 if and only if the chromatic number of G is less than or equal to k. If the chromatic number is bounded above by k, that means that this thing is positive. So the question is, how hard is it to compute this number for a completely generic graph? And And the answer is that for a completely generic graph, this is a harder thing to do. For well-known graphs and simpler graphs, this is not so hard to compute, but just computing it completely generically is more difficult. But so Birkhoff and Lewis figured out a way to reduce this problem to something that was easier, something that was more manageable. So I'm going to give an example first, and then I'm going to define the actual quantity that makes this a lot more manageable. So quick definition. So let G be a graph and E an edge of G. So recall that G minus E is the edge deleted from G. So recall the definition of G minus E, and define we're going to write it like G mod E. Okay. And I might even say this in words, G mod E here. Define this to be the graph obtained from G by removing E and identifying the end vertices of E, basically leaving only one copy of any resulting multiple edges. So define G mod E to be the graph obtained from G by deleting E, identifying its end vertices, leaving only one edge behind from any resulting multi-edges. What do I mean by that? Let's show a picture to see what this does. So, consider on the left the graph G. G with the edge BC deleted is this graph. So this is just normal edge deletion here. So I've just removed this edge BC. Okay. G mod BC, however, collapses this, what was an edge, B and C get identified, meaning they become the same vertex in the graph. But notice what this would cause if we just did this on its own. Technically, when you identify B and C, you would get now two edges emanating from that same point that you've identified, because there's an edge going from B to A and an edge going from C to A. So when you did this identification, technically, you would get one edge going from this point from C to A and another edge going from B to A. So you would get multi-edges between this point and A. But what you do is you throw away any multi-edges, leaving only one. So in this collapsed graph, only one edge remains between this collapsed point where you're identifying B and C here and A. Okay? So right, if you just did this operation without this fix, there would now be multi-edges. There might be some contexts where that makes sense and that's fine to do, but since we are generally considering graphs that don't have these multi-edges, because of this, we're not allowing that. So we're getting rid of all but one of these edges. Okay, everything else behaves as normal, right? These go together, and now Because B was adjacent to W and C is adjacent to Z, this collapsed combined point is adjacent to both W and Z. Okay, they were separately adjacent to A. They remain adjacent to A through a single edge, not a multi-edge. Right? B was adjacent to X, C was adjacent to Y. This collapsed point is adjacent to both X and Y. So this is what this operation does. So understand this before moving on to what I'm going to define now. Okay, draw some of your favorite graphs and do that operation. So, there is the following theorem. Let G be a graph and let E be any edge of G. Then the number of distinct colorings using K colors on G is the same as computing this number for the graph G minus E using K colors and subtracting from it the number of distinct colorings on the graph G mod E, again using K colors. Okay. So the proof of this is actually short, but I will leave it to you to read through. So the proof of this is on page 98 and 99. It's only like a 2-paragraph proof. It might not be clear immediately why this is a thing that makes our life better or easier in computing this number. But we're going to see how this works. Okay, so the question, like, how does this help us? To see an answer, let's consider specific graph. Let's consider like a path on 4 vertices. So maybe let's draw path on 4 vertices on the next page. Okay, there it is. And suppose that we are trying to find the number of distinct colorings on the path on 4 vertices using K colors. Okay, so how many ways are there to color the vertices of piece of 4 with K colors available? That's what is being asked here. Okay, so let's label the edges here. Instead of labeling the vertices, I'm going to label the edges here. There's 3 edges, right? E1, E2, and E3. Okay. By this theorem, let me just flash it on the screen again. This thing that I've boxed, right? And it's fine if you need to keep referring back to this. You can't keep it in your head immediately because until you get used to this notation and how this thing works, it might be a little bit confusing. By the theorem, what can we say? We can say that whatever this is the number of distinct colorings using K colors on the path on 4 vertices. This is the number of distinct colorings on the path on 4 vertices minus an edge, let's say E1. Minus the number of distinct colorings on the path on 4 vertices mod that first edge E1, again using K colors here. Now, we are going to use subsequent operations on these, so I'm going to write these using this notation here, but then I'm going to quickly use other letters to denote these, just because if I kept using this, it would get really, really nasty, as you'll see. So, so this is a good thing to do at this step. Whenever you're doing this for a graph, this is a nice thing to take into consideration here. So, first of all, what does path on 4 vertices minus the edge E1 look like? Of course, we know what that looks like. It looks exactly like the path on 4 vertices, except I've taken this edge off, and now I still have E1 and E3 here, but edge 1 has been deleted. Here's what it looks like. What does the path on 4 vertices mod the edge E1 look like? So remember how this operation works. I would remove the edge E1, identify its endpoints, remove any multi-edges down to a single edge if I need to. Well, here, removing that edge, identifying the endpoints, just basically collapses this edge entirely to this point. It crushes this edge to this point and identifies it. So this would be this graph. Now, I am going to define this to be a graph I call G11. I'm going to define this to be a graph I call G12. Again, you'll see why I'm going to do this. So, here's my thoughts. Of course, my thoughts are, well, I'm trying to compute this number using this theorem. And by the theorem, I'm now computing this number. Relabeling this relabeling I'm doing, I'm going to rewrite this. So the number of colorings on the path on 4 vertices using K colors is, by the theorem and using this relabeling, this is the number of colorings on G11 using K colors minus the number of colorings on G12 using K colors. But now I want to use this theorem again. And when I say this theorem, of course, I mean the generic theorem here, that the number of colorings on a graph G using K colors is computable in this way. So it's the number of colorings on graph minus edge using K colors minus the number of colorings on graph mod edge using K colors. So I'm using this again for each of these terms. So for the first term, this would be the number of colorings on G11 minus an edge, we'll say E2 here, using K colors, minus the number of colorings on G11 mod the edge E2 using K colors. These two terms come from just this, right? So these two terms are my application of the theorem to this single term. Similarly, now I have this minus sign applied to, I'm going to go ahead and distribute the minus sign. So if you're curious why the signs work out this way, this is minus the theorem applied to this, which is minus the number of colorings on G12 minus the edge, we'll say E2 using K colors. And then minus minus, so plus the number of colorings on G12 mod the edge E2 using K colors. So these two terms come from applying the theorem to this and distributing the minus sign. Now you see why I relabeled these. Right, so now you see exactly why I relabeled this business. Because, well, having p sub 4 minus e1 parentheses minus e2, that's what would have to be in a subscript here. That's really annoying. And then I would have p sub 4 mod e1 minus e2 in another subscript, right? So it's better to relabel these at these steps. Also, this helps you to see how this could be amenable to computation, right? So you probably I think pretty much all of you are CS people, so you're probably already thinking how you could have this be generated by some block of code, which is good. That's the point, to see how this works. Okay. No, let's see what these things actually are. So what is G sub 1 1 minus E2? So G sub 1 1 minus E2. That is the graph that, so it's this, here's G sub 1 1 minus E2. I'm now taking away this edge. I have a single edge left in my path now, E3. And what does G sub 1 2 minus E2 look like? Well, here's G sub 1 2, so it's this. Okay. What about G? Maybe I should box these so that we don't get our labelings confused. What about G sub 1 1 mod E2? You might ask, like, what am I doing at this step, right? I'm drawing a picture of all of these graphs. There's like 4 of them, right? There's G sub 1 1 minus E2, shows up here. G sub 1 1 mod E2. There's G sub 1 2 minus E2, and G sub 1 2 mod E2. Okay, so I'm doing all of them. G sub 1 1 mod E2, what is that? So I take G sub 1 1, mod E2, I delete E2 and identify the end vertices and remove any multi-edges, leaving a single edge if needed. Here, that's just collapsing this. So this actually looks like this. Well, interesting, right? Because we actually see, Okay, let's do this last one. So what does G sub 1 2 mod E2 look like? Here's G sub 1 2 mod E2. I delete E2, identify its end vertices. There. You see how we're reducing this in a way to where we're eventually going to end up with, we're going to terminate and be left either with a single vertex where it's obvious how many colorings there is, or a bunch of disconnected vertices in this case, where again it's going to be obvious how many colorings there are. So eventually this question is going to be obvious. Like, we're going to reduce this into a bunch of pieces, and each piece is going to have an obvious number of distinct colorings. And so that's the idea. That's how this makes our life simpler. You might have seen the applications of this theorem and said, oh God, this just seems like it makes it a lot harder now because you've replaced one graph with like 6 graphs. But we're going to get down to a point where every single term in this expression is going to be something that is very easy to compute the coloring of. That's the idea. Let's relabel these. Let's call this one G21. Let's call this one G22. And we can call this one G23 and this one G24. Okay. But let's go one step further. Let's apply our theorem one more time. Well, multiple times here. Apply theorem again to each term. When I say each term, I mean all four of these. The theorem, again, here it is, takes a single term, splits it into two, is this difference. So I should get 8 terms when I do this. Okay, but what I want you to note is what happens at every step. So before I even apply the theorem and write it out, I know what I'm going to do, right? The remaining edge in each of these gets either deleted or modded, right? So note, and I'm gonna bring this sheet back. Note, in each case, the sole remaining edge gets either deleted or collapsed, which we've been calling modding out. But what happens when I do that here? If I take this graph, G21, and delete the remaining edge, what do I get? G21 minus the remaining edge, what do I get? So notice G21 minus the edge E3. What graph is that? So here it is. I remove E3. What graph do I have now? The empty graph on 4 vertices. We know how to compute the colorings on that. Okay, next. What about G21 modding by E3? So I take G21, and again, applying the theorem means I'm going to have 8 terms, right? Those 8 terms correspond to doing each of those 2 operations, edge deletion and edge collapsing, on the remaining edge of each of these boxed graphs. So I'm doing it twice here, twice here, twice here, twice here. That's 8 total terms. So I'm just checking. This is like a roll call of what graph results when I do this operation, right? So here now, instead of deleting the edge, I'm collapsing it, right, or modding it. So instead of deleting this edge, I'm modding it. So I'm taking it, I'm squishing it to a single point, identifying it, removing any multi-edges if I need to. Because I've removed this, that's the last edge. Now that I squish them, what do I get? I get 1, 2, 3 vertices. This edge gets deleted, these 2 vertices get squished and identified. So 1, 2, 3, the empty graph on 3 vertices. There are no edges left. Okay, what about G22 minus E3? G22 minus E3 leaves me with the empty graph on 3 vertices. What about G22 modded out by this edge E3, collapsing the edge E3? Here's G22. If I collapse this edge. That's deleting E3, identifying the end vertices. It leaves me with two disconnected vertices, the empty graph on two vertices. Okay, let's move on to G23. G23 minus E3 is what? Here's G23 minus this last edge is the empty graph on three vertices. G23 with the last edge collapsed is, again, because this is the same graph, we already knew this. Take E3, delete it, identify the end vertices. This is the empty graph on two vertices. What about G24? G24 minus the last edge is the empty graph on two vertices. I just take away that edge. G24 with that last edge collapsed. I remove that edge, identify the two vertices to a single vertex. That's it. I'm left with a single vertex, the empty graph on one vertex. So this last application of the theorem to each term in what I have, this is it. I now have no edges left to remove or mod out by. Right? I have no edges left to remove or collapse. So that's it. We're done here. Okay. And so what I get, the final step of this process, on the left-hand side, of course, I had the colorings using K colors on the path on four vertices. This was the thing I was trying to compute. If I write out all of the terms here, what does this look like? So here I'm writing out all my terms. This is the number of colorings on G21 minus E3, which is the number of colorings on the empty graph on four vertices using K colors, minus the number of colorings on G21 mod E3, which is the empty graph on three vertices. Again, using K colors, it's using K colors on all of these. Right now, again, this is minus plus, so it's minus, because the minus sign is distributed here. The number of colors, the number of colorings using K colors on G22 minus E3, but that is the empty graph on three vertices. Plus the number of colorings on G22 mod E3, which is the empty graph on two vertices. Minus the number of colorings on G23 minus E3, which is the empty graph on three vertices. Plus the number of colorings on G23 mod E3, which is the empty graph on two vertices. Okay. Then plus, again, because of the minus sign, this would be plus the number of colorings on G24 minus E3, which is the empty graph on two vertices, minus the number of colorings on G24 mod E3, which is the graph, the empty graph on one vertex. But we know what the number of colorings on the empty graphs are. Right, this is like the second class we computed. For all k and n, the number of distinct colorings on the empty graph on n vertices using at most k colors is k to the n. So what is this? This is k to the 4 minus k cubed minus k cubed plus k squared, minus k cubed plus k squared plus k squared plus k. So combining like terms, this is k to the 4th minus 3k cubed plus 3k squared minus k. Okay. So, what does this allow us to do? I want to check some things. So, let's check. According to this, what is the number of colorings on the path on 4 vertices using one color? According to this formula, so we know what this should be. This should be 0. But let's use this formula. This would be, here, I'm just going to leave this on screen. Okay, so there it is. This would be 1 to the 4th minus 3 times 1 cubed plus 3 times 1 squared minus 1. This would be 1 minus 3 plus 3 minus 1. This is 0. That checks with how this should be. What about using two colors? This is 2 to the 4th minus 3 times 2 cubed plus 3 times 2 squared minus 2. This is 16 minus 3 times 8, so minus 24, plus 3 times 4, so plus 12, minus 2. So this is 26 minus 24. This is 2. Is this true? Well, let's just see. So let's say I have two colors, red and blue. So if this is red, this needs to be blue, and then this needs to be red, and this needs to be blue. Okay. What's the next number? Well, if this is blue, and I chose blue here to make this different from this vertex, then this needs to be red, then this needs to be blue, but then this needs to be red. And those are the only two. Okay. This, it's obvious now. Sorry, this is minus k. It's called a chromatic polynomial. And in this instance, it is the chromatic polynomial for P4. So I should say the chromatic polynomial for P sub 4. Okay. Now, here is the thing. So first thing to note is the following. So note, we don't always need to go all the way down to empty graphs. So what is an example of when you would be able to stop before getting all the way to an empty graph? Just think for a second. When might you be happy stopping early, we'll say? Well, in this process, let's bring some of the steps of the process back. You can see them on the page. Yeah. So if we're looking at this, if in this process, when we start doing these operations of edge deletion and edge collapsing, if we get to a graph that we already know the chromatic number of, we don't have to keep going, or sorry, the chromatic polynomial for, we don't need to keep going, we can just write out the chromatic polynomial for that part. So for instance, maybe at this step, you see this and you're like, oh, actually I know the chromatic polynomial for this graph. Like, this is my favorite graph, this is the fun graph, this is what I call the fun graph, and I already know the chromatic polynomial for this because I've dealt with this graph so much because I love it so much. Right, so I already know what the chromatic polynomial for this is. So at this step, I can actually stop and then just do, I don't need to do anything else on that term. And then this other term, maybe I don't know what that graph is and I have to take it all the way to the empty graph. But the point is, if at any point you have reduced this, if you know the chromatic polynomials for each of the terms, then combining them together it is no problem at all. That's the idea. The idea is you don't have to always go all the way to the empty graphs, but of course, if you do carry this process through, it's nice to at least know that it does terminate at a step where all the graphs are empty, and thus it's very not just deterministic. It's we know exactly what each term has to look like, and then it's just a matter of doing some very basic algebra to combine the terms and get your final polynomial. So we're going to end this section with some facts here about the chromatic polynomials. So the following theorem, which you can think of as facts about chromatic polynomials, let G be a graph of order n. Then 1, this object, the number of distinct colorings of G using at most k colors, is a polynomial in K of degree n. Was our piece 4 chromatic object of degree 4? Yes. So piece of 4 is a graph on 4 vertices, and yes, indeed. Because, of course, where did this k to the 4th come from? It came from at that last step. You had removed all of the edges. Again, going back, leaving yourself with an empty graph on 4 vertices. And one of these terms, you are not going to have any collapsing going on, right? So in one of these terms, no collapsing happens. That is the term that is the leading term. On the smallest term, there's going to be maximal collapsing down to a single vertex. Now, what I'm doing for you in words here is actually proving the various parts of this theorem, but this is why it's true. The proof of this theorem is going to be an exercise or maybe something on your exam that I post on Friday. But this is what's going on. So here, the reason the leading term has degree 4 is because you are going to always end up with an empty graph on the same number of vertices that you started with. Because in that part of the process, starting here, in that part of the process, you're not collapsing at all. You're only removing edges. So yeah, you get to the last step and you have an empty graph on 4 vertices in that example. So yeah, this is polynomial nk of degree n. That always works in this way. The leading coefficient is 1. Again, that's because there's only one of those various graphs that remains uncollapsed, right? There's only one of those that doesn't get hit with a collapse at some point. 3, the constant term is 0. Does that mesh with what we have seen here? Yeah, there was no constant term. Every term had a k in it. So the constant term was 0. And that's always going to be how these work out. Again, consider why this is. It's because in the maximum collapsing that happens, you're going to get down to a single vertex, no less. You're always going to have at least one vertex, so there's always going to be a k there. Next, the coefficients alternate in sign. So it's plus, minus, plus, minus. I know I screwed that up and had to here. It's really a minus. So they always alternate in sign like this. Okay, you can think about why that one is. Here is the thing that you may have noticed when we were piecing these together from the terms themselves, when we were combining why there were 3 copies of some and 1 copies of the others in that example that we just did. But the absolute value of the coefficient of the k to the n minus 1 term is the number of edges in G. Let's see that that works in our previous example. Here is the k cubed term. That's the k to the n minus 1 term in this example. Its absolute value is 3. Are there 3 edges in P sub 4? Yes. Right, we started with 3 edges. Now, that's a nice fact to have. This isn't super deep, though. Think about why this is. Think about why this is. In that example we just did, follow the process and how we perform these operations on the graph, and think about how each of these terms, going back to here, think about how each of the terms that gave us a k cubed, so here was one of them, here was one of them, here's another one. Think about how these terms are enumerating the number of edges. Here you were subtracting, you were deleting one edge. Here you were deleting another edge. Here you were deleting the last edge. Think about that in the process of why. This is essentially enumerating how many edges you have to delete from the graph G to make it the empty graph on n vertices, but the number of edges you have to delete from a graph of order n to make it the empty graph on n vertices is just the number of edges in the graph, right? So that's what it is that's going on here. Proof. You do it. None of these is super tricky. In fact, the words I said while I was explaining each of these things is basically the proof for each step here. Okay. So one more thing I wanted to note: when Birkhoff considered these chromatic polynomials, he considered chromatic polynomials of planar graphs, and he hoped that he found one of them that had 4 as a root. Okay, because if you'd found one, that corresponding planar graph would not be 4-colorable, and thus it'd be a counterexample to the 4-color theorem. So that was the idea. So this, of course, did not work to prove or to find a counterexample to the 4-color theorem. It also wasn't it wasn't possible to show that 4 couldn't be a root, thus proving the 4-color theorem. That there's neither of those was successful, but this is a very nice like counting technique on these graphs that has other applications. This is just a very nice thing that ended up not being useful for the original purpose, but still useful in other ways. Okay. So, the next thing that I want to discuss in like my last 14 or so minutes of lecture is the notion of matchings on a graph. So now we're on to something completely different. I'm going to read off a following potential application problem here. I'm not going to draw a picture of it. The first example we'll see of a matching is going to be more visual, but this is an example of what a matching or how a matching might arise. So, the Senate committees that we discussed previously in either last lecture or the lecture before, I can't remember, need to form an executive council. Okay, each committee needs to designate one of its members as an official representative to sit on the council, and council policy states that no senator can be the official representative of more than one committee. So, for example, suppose there are 4 committees. Senators A, B, C, and D are on Committee 1. Senators A, E, and F are members of Committee 2. Committee 3 consists of E, F, and D, and Senator A is the only member of Committee 4. So in this example, the Executive Council could be A, E, F, and C, which would represent Committees 4, 3, 2, and 1, respectively. But if I alter my example a little bit, let's say Committee 1 consists of letters W, X, and Y, Committee 2 of W, X, and Z, Committee 3 of W, Y, and Z, and Committee 4 of X, Y, and Z, Committee 5 of W and Z. Here, toying around, and again, until you write all of those things out as I'm going along, it might not be obvious trying to keep all those letters clear in your head, but you'll see that it's impossible in this case to select official representatives according to this policy. You would have to have someone being a representative for more than one committee. So that's it would be impossible to do it in this case. So then the question is, under what circumstances can the executive council be formed successfully? This is answered by what we are going to consider, which are matchings in a graph. So what is a matching in a graph? Quick definition. A matching in a graph is a set of independent edges. What does independent edges mean? So a set of independent edges, what is that? That is a set of edges where no edges share a vertex. Or let's say no pair. Just to illustrate what is going on here. Okay. This makes it easier to consider this, thinking of it as a pairwise comparison. Okay. So no pair shares a vertex here. So set of edges, no pair shares a vertex. If so, given a matching, we'll call M of a graph G, the vertices belonging to the edges of M are said to be saturated by M, or M saturated. So the vertices belonging to edges in M are said to be M saturated. Or saturated by M. The other vertices are M unsaturated. Okay. One more thing. If a matching M saturates every vertex of G, it is said to be a perfect matching. Okay. So, before I actually, yeah, maybe I'll go ahead and just define the rest of the terms and then give you a bunch of examples. So, a maximum matching in G is a matching that has the largest possible cardinality Now, cardinality of a set here, this is a set of edges, so this contains the maximum possible amount of edges. A maximal matching is a matching that cannot be enlarged by the addition of any edge. Okay, so let's do some examples here. We'll bring all these terms back. So the first example that I want to do is the following. I'm going to bring this book over. Okay. Let M1 be the matching that is denoted here as A, B, C, E, D, F. So it contains three edges. They're highlighted in bold black here. So A, B, C, E, and D, F. That is a matching. Okay. M2 is another matching, which is CD and AB. Okay. M3 is the matching consisting of the single edge DF. Okay. We could say that A, B, C, and D are M2 saturated. A, B, C, and D all belong to M2, right? So they are M2 saturated. E, F, and G are M2 unsaturated because they are not vertices showing up in M2, right? The only M1 unsaturated vertex is G. So the matching M1 that is given in bold here, the only vertex it doesn't touch is G. So it's not a perfect matching because it doesn't saturate every vertex, but it is a matching that saturates every vertex except for one, except G. Okay. Now let me draw a graph. So I'm going to draw following. Let me label these vertices. Say this is A, this is B, this is C, this is D, this is E, F, G, H. Okay. Here's the question. We'll call this graph G1. Does G1 have a perfect matching? You can pause the video and see if you can come up with one. The answer is yes, it does. See if you can see it. Right? So CH, AB, DE, FG. Right? That is a collection of independent edges that saturates every vertex of the graph, right? Every vertex is the endpoint of one of those edges. Okay, and those are all independent. They don't pairwise share any vertex. So G1 has a perfect matching, so the answer is yes. Okay. Here, to illustrate a maximal and maximum matching, let M1 be the matching AE. Where do I want to put this? Oh, let me draw another picture here to do this. If I'm going to show both of these, I need a different graph. This won't do it, so hold on 1 second. Let me call this graph G2 here. So me. And one more. There we go. Okay, so let me label these A, B, C, D, E, F, G, H, I, J. Oh, I need one more edge here. Okay, now I'm good. Okay, so here's graph G2. Let M1 be the matching AE, BF, CD, GH. So AE, BF, CD, GH. That's the matching. Okay. So this is an example of a maximum matching. Right? So why? Well, the reason that it is a maximum matching is because we know that because of this claw thing going on here, right? Only one of these edges can show up, right? So of these three edges here, only one of them could show up in a matching, because if any of the others showed up, then they would share a vertex. It wouldn't be independent, right? So only one of these can show up. So one of these showing up, and then of the remainder, right, there's nothing else to add here, right? Any other addition of an edge would include a vertex already included here, so this is truly the maximum cardinality this thing can have. Okay, and you can convince yourself of that by draw this yourself and try to find a larger matching that there's 5 edges instead. Okay, let's do another matching. So M2 is, we'll say, DG, AF, and BC. So here, just to highlight it, this is DG, AF, it's this one, and BC. This only has 3 edges versus M1 having 4, so this is not maximum, but is maximal. I know this is confusing. This is the terminology decided on. Why is it maximal? It's maximal if you can't increase this matching by adding another edge. And the way that we've selected the edges here, so DG, AF, and BC. The way we selected those edges is in such a way, because DG is included and G is included, I can't include any of these edges because they would share a vertex with G. So that gets rid of those 3, can't possibly be added. Okay. Because I have AF added, I can't include any edge that has A or F as a vertex. And because B and C are added, I can't include any edge that has B or C as a vertex. And that really limits what I can do here, right? Because E is only, so this E is adjacent to A and C, and that's it. So that edge is removed. This other edge I can't throw in, this edge I can't throw in, so because D is included here. So I cannot add another single edge to this matching and have it still be a matching. So it is maximal in that sense, but it's not maximum because there's only 3 of these things. So that is the reason for the distinction. If you were wondering why we had a distinction like this in the first place, this is the reason for something like this. Okay, so that is, we are almost exactly at an hour and 20 minutes, so I'm going to stop here. And this is perfect timing because we finished the section on matching, so that takes us exactly where we want to be, talking about Hall's theorems and SDRs tomorrow. So we'll do that in tomorrow's lecture. We are essentially going to be finishing the graph theory portion almost entirely this week. We might need to do like a little bit of Ramsey theory like next Monday instead, but after that we are essentially done with the graph theory portion at almost the exact halfway point in the course, which was the intended pace. That was the intended result there. So after that, the remaining half of the course will be mostly combinatorics, and then whatever little bit we might have at the end, we might do an application of both of these things, graph theory and combinatorics, to infinite graphs. So that's the plan. We are exactly on pace. So anyway, that is all for today. So as always, let me know if you have any questions about the homework or anything like that. Email me whenever you want to. I'm gonna have another problem session on Friday after lecture for a bit. So if you have any questions about that homework, let me know. And yeah, anyway, that is it. So I will see you all tomorrow.